Many of these work here under section 1.2. It's covered in school, but of course, probably you've done some of this work many years ago. You may have forgotten it. And then there's the notion of algebraic expressions, rational expressions, equations, modeling, inequalities. So I'll probably have a look at that. And here and there, if a person feels that I need to jump to functions and just verify some stuff, that's also fine, okay? Last time I checked, no one started with work beyond chapter 2. So, but if there is such a person, well, they're at liberty to ask me, okay? So what I'm going to do is briefly go through the definition of an absolute value. But like I said, if you guys, you are free to ask a question that you dealt with beyond section 1.1, okay? So just for the sake of completeness and just to fill maybe gaps, you might have done this section, but there may still be gaps lurking. So let's just have a look at the notion of absolute value of a number, okay? So here A is a real number, and I hope it's big enough for you guys to see. Here A is a real number, and the absolute value of A is those two vertical line segments there. The absolute value of A is defined as A if A is greater than 0, and negative A if A is less than or equal to 0. So it's defined in two ways. On the other hand, like I stated earlier, this definition here is also plausible here. The one that says, or as the absolute value of A equal to A, if A is greater or equal to 0, minus A if A is less than 0. What you should notice, guys, is that the absolute value function is always positive or 0. It's never negative. You should see that. Okay? So in the first instance, just see if I can do something here. In the first instance, if you look at the definition, it says absolute value of A equal to A if A is greater than 0. Well, A greater than 0 means it's positive, right? It's a positive function. On the other hand, absolute value of A equal to minus A if A is less than or equal to 0. Well, if A is less than 0, a negative times a negative is a positive, right? There they say it's minus A. On the other hand, if A is equal to 0, well, minus A will become 0. So you will see that the absolute value function is always greater or equal to 0. So it's never negative. And the same applies to the second definition, which is equivalent to the first one. Okay. Right. Are there any questions at this stage, guys? You're fine with that statement? We can look at example 1.1.1. I'll entertain questions that you may have on this one. Let's just go through this little example here. Let me just see if I can add some color to this thing here. Yeah, let me just see if I can have some color here. Right. Let's look at this example here, guys. Let's look at this example here. I need to refine it a bit. Okay. See if I can make it a bit thin. It's a bit thick. Okay, yes, let me just make it a bit thin here. Sorry for that, guys. I'm just going to make this a bit thin. Okay, so let's look at this example here, guys. Here they say write the absolute value of 2x plus 3 without absolute value signs. Okay, without absolute value signs.
I'm not seeing you, Dr. Sears.
Hello?
My apologies. Not sure what you're referring to because we still have the study guide on the screen. Page
yes, example 1.1.1. Yeah.
All right. If you can please scroll down a bit, then we can see it.
Oh, okay. Wow. That's interesting. Wait. What do the other people see? Because they must share again.
No. You just need to scroll down on the document.
Okay. Yes. So on top, you should see the example 1.1.1.
Mm-hmm.
Do you see that?
Yes. And now
so I'm
further than that.
Yes, I'm referring to this example after I've discussed the definition of absolute value, what it means. Okay. So now we'll apply the definition to this problem here, absolute value of 2x plus 3. Okay. They want this written without absolute value signs. So what they do, they take you back to the definition, which I'm ticking there. They remind you, so our A in this case is 2x plus 3. So here they remind you that by virtue of the definition, absolute value of a is equal to a if a is greater or equal to 0, and it's negative a if a is less than 0. So now they replace a with 2x plus 3. So if you look at this definition here, there we keep the a, we keep it as is there, circle it. And here my a is 2x plus 3 inside that, inside the absolute value sign. So the definition says the absolute value of a is equal to a if a is greater or equal to 0, and negative a if a is less than 0. Like I said, you'll always notice that the absolute value is positive or 0. It's never negative. Okay. So now what they do is, instead of writing a, you've got 2x plus 3 in that absolute value sign here. So I'm just starting with this. That's what we're referring to. Okay. So you will look at the definition there. They retain a there. So here we retain 2x plus 3 takes the place of a. And if you look at the definition with a, the absolute value of a, it's greater or equal to 0. So a is equal to a if a is greater or equal to 0. So by the same token, we retain the 2x plus 3 inside the absolute value line segment. And you can see it keeps that, just like we do for the definition here, just like that. So, and that is true if 2x plus 3 is greater or equal to 0, that part. So let's entertain this part quickly before we look at the part below, before we look at this part here, okay? The one that I cross out. Let's first look at the top part there. So 2x plus 3, right, is greater or equal to 0. And this is only true, well, if you transpose a, you take it to the right-hand side, it becomes minus 3. So you have 2x plus. So you've got 2x greater or equal to minus 3. And you divide by the 2 there to get minus 3 over 2. In the same way, if you look at the second part of the definition, the absolute value of a is minus a if a is less than 0. This part here. And this is the part here. So now this 2x plus 3 inside here, this becomes minus open bracket 2x plus 3. And this is true if 2x plus 3 is less than 0. Okay? Right. So if you multiply out this minus here with 2x plus 3, let me just highlight the pen again. This part here. Okay. Can everyone see that what I'm highlighting there, guys? Guys, can you see what I'm highlighting there? Hello?
Yes.
Okay,
yes.
great. So that negative sign outside in the definition, where absolute value of 2x plus 3 is equal to minus times 2x plus 3. Now we're using that part. And we multiply the negative by the 2 terms inside, and we have minus 2x minus 3. Okay? And of course, if we transpose the negative 3, it becomes a positive 3, right? And then we divide by negative 2, which means the inequality changes now to less than instead of greater than. Okay? So because I'm dividing by minus 2. So let me just see that. So if you say it's minus 2x minus 3 less than 0. So let me just try and write this here, guys. Let's make it very thin. So if you look at this part here, so it becomes minus 2x minus 3 if x is less than minus 3 over 2. They get it from this part here. So let's just go to that part again. So we had the absolute value, so 2x plus 3 is equal to 2x plus 3 using the definition. If 2x plus 3 is greater or equal to 0 or just greater than 0, it doesn't matter, okay? I can say that, or I can just say greater than, it doesn't really matter. And it's minus 2x plus 3 if 2x plus 3 is less than 0. This is true. The first one is true. If we do our transposition there, if x is greater or equal to minus 3 over 2. From here, you can see that. From here, okay? By the same token, this implies, so if this is correct, and you transpose the 3, this is true if x is less than what is this? Minus 3 over 2. Does everyone follow that step, guys? Remember, I've transposed the 3 here to the right-hand side of the inequality, and then I divided by 2. So that without the absolute value sign, you have these forms here, and it's subject to these conditions here. Any questions there, guys? Is that sufficiently clear?
Okay, good afternoon, everyone. I have a question.
Okay.
So, on the inequality, okay,
Yeah.
the one below, the negative one.
Yes, yeah.
Why can't we solve it and then write x is less than 3 over 2? Because when we solve it, okay, we're going to distribute that negative sign. We're going to have negative.
Okay, I'm doing it as you speak. Right?
Oh.
I'm doing it as you speak. Right?
Yes.
Right? And I divide by a positive 2. And knows that the inequality doesn't change direction. If it was a negative, if I divide by a negative, it would change direction. Sorry, okay? So there's it. That's what you wanted, right? Right.
Oh, I'm asking. Why are we not solving that negative a? When we solve
one,
it, yeah, we're going to get negative 2x and negative 3.
You're talking about that one, okay? No, yeah. For the condition where x lies, you must use the definition.
Oh, okay.
You must use the definition. It's a good question. It's a good question. Absolute value of x is equal to x if x is greater than 0 or greater or equal than 0. Doesn't matter. Equal to negative x if x is less than 0 or less than or equal to 0, right? You choose one or the other here or there, okay?
Oh, all right. No problem. Thank you very much for that clarification.
Here's some examples, additional exercises here. We can perhaps look at number C there, if it's okay with you guys, minus 5x plus 4. Write each of the following without absolute value signs, okay? Can you guys see the screen there? Guys, can you see the screen?
Yes.
Yes.
Great. Okay. So what I'm proposing is, let's look at C there, 1C, okay? Let's look at 1C. Write each of the following without absolute value signs. Remember, the one that we just did now, ultimately you write it like this. This is how you ultimately write it, like this, okay? You'll multiply out the negative as the previous person suggested. But of course, we don't use that directly to establish. Remember, we came to this. This was the wrong part, right? We did this. That's what we ended up with, right? They say the following is incorrect. Here, the person assumed this to be x and assumed this to be minus x. Can you see that? Hence, the person wrote that. That's why they say the following is incorrect here, okay? But this is where we ended up with, yeah. We follow that type of reasoning there, okay? Applying the definition. Here was a wrong application of the definition, right? So let's do the other one now that I proposed. Let's do this one here. Minus 5x plus 4. So let me just do a screen share again. Just do a screen share again. Minus 5x plus 4. So our question was this. I think it was minus 5x plus 4, if I'm right, guys. The question, right? Okay. Let me just write the definition here. Absolute value of x is equal to x if x is greater or equal to 0, and it's negative x if x is less than 0, right? So let's look at this one. We will say this one is equal to minus 5x plus 4, right? If minus 5x plus 4 is greater or equal to 0, and it is equal to, now I'll multiply by negative. I'll multiply by negative, okay? It's minus 5x plus 4. Remember this here, guys, right? If minus 5x plus 4 is less than 0. So if I look at the first one here, the condition there, I'm trying to do it simultaneously, but let me look at the top one. So it's minus 5x plus 4 without absolute value sign. If now I'm solving this part here, as the previous person suggested, okay? I'll be careful here. I will have division by -5 here, which means the direction of this inequality will change here, okay? So I will transpose the 4 to the right-hand side, will become -4, and I'll divide it by -5, and the direction of this will change here, okay? That will change. So that ultimately, it will become like this. I want you guys to think about it. Does everyone agree with that for the top one, for this one here? I've transposed the 4 for the top one to the left-hand side, it becomes -4, right? I took it to the right-hand side. Then I divided by -5. Division by a negative means the direction of the inequality will change. That's why I end up like that, okay? In the same manner, if I multiply out this negative here, well, I get 5x -4. Now I use this. Now I use that. The one that I tick here, this one here, I use this now. I use this part here. I work with this now. Again, I transpose the 4 to the right-hand side. It becomes -4. And I divide it now by -5 so that the direction of the inequality will change now. So it will be greater than 4/5. That's all. Any questions there, guys? Can you hear me, guys?
Yes, we can hear you, sir.
Okay.
I do have a question.
Yeah, my question is first, do you follow my sequence of reasoning there by virtue of this definition that I'm using? Remember, I'm just using this definition, right? And I'm doing it one shot. I'm doing it quickly because you've done the previous example slowly. So now I'm just using the definition straight away, okay? Remember, I did the transpositions. When I divide by a negative, inequality direction changes. That's all you have to bear in mind. So this is the condition for the top, and this is the condition for the second part. Okay, what is your question now?
Okay, my question would be for the second one.
When you say the second one, the bottom one. You're saying
yes,
the bottom
one. The bottom one.
This one here. Okay.
When you multiplied -5 with the negative, it became 5 minus 4, 5x minus 4.
Yes. Yeah, to get this, yeah.
And then for the if part, do we not use 5x?
No, you don't use that. You use this, you use the original thing inside here.
We use the original.
Look there. The definition.
Oh,
Look there. Sorry.
Okay.
I use that in the definition. Sorry. Can you see that?
Yes.
It's like the previous person asked me the same type of question, okay? Because he asked, why don't I use that? But if you look at the definition doesn't use this. It uses the original x. Can you see that? It doesn't use the -x. Okay?
Okay.
Good question. Just bear that in mind. I always used to bet at school with this. And then, as you suffer, you begin to realize that you were wrong. And you look at the definition. In mathematics, the definitions will always tell you what to do. Okay? You just have to, and people, you must know this throughout your mathematical careers, you must know that you always look at the definition if you want to solve a problem or try or attempt to solve a problem. It helps you a lot to know what the definition means, okay? And also statements of theorems, conclusions of theorems is very important. Of course, combined with that, you need a good memory also, okay? And as you age, it becomes a bit more difficult, but it's fine. Okay, right. Any other questions, guys? So we looked at that problem, -5x plus 4. This is the one we covered. Okay. Let's go on to exponents and radicals now, if there are no other questions. So you guys can attempt, maybe the next time when you see me, you can maybe look at any of those other 3 problems here. Any of the other 3 problems there. and do it similarly in a similar fashion, okay, as I've done it, okay? Right. Can you guys see the screen, the exponents and radicals?
Yes.
Okay, great. So maybe I should ask you guys, rather than belaboring the issue here for other people, because I would like to entertain other people too with their sections, okay? So were there any problematic problems here that you encountered under algebraic expressions? Let me just mention also. This one is, I suspect that this one is examinable, right? This is examinable. Exponents and radicals. So let me just go to that section. Exponents and radicals. Okay, let me just note the laws of exponents. And maybe just have some results on the radicals also. Okay. Let's just look at that, exponents and radicals. People, you have these laws of exponents that you guys are familiar with. Yeah, A, M, and N are real numbers, okay? Well, they can be natural numbers also, but a real number, remember, the natural numbers are contained in the real numbers, okay? So when the bases are the same, these are some of the main aspects that you need to be familiar with. And then if you have some power a to the n, and you raise it all to the exponent n, then you just multiply the inner exponent with the outer exponent. And then there's these other rules that say a to the minus m. You can write it as 1 over a to the n. Of course, here we don't assume that a is 0, and because division by 0 is not permissible. And then you guys, of course, assuming a is not equal to 0, a to the 0 is equal to 1. You guys have encountered those laws of exponents, right, guys? Would that be a fair statement, guys, that you guys have encountered those things?
Yes.
Yes, you are familiar with it, right? And look, there are several others and variations of it. So let me just add 1 prime maybe for radicals. Let me just see there. For radicals, you also have this thing of the nth root. Let's say I call it 1 prime, okay? Let's say the nth root of a. So what number must be multiplied by itself n times to get a? In exponential form, you can write it like this. You guys know that, okay? Of course, what does this mean? If I say to you the nth root of a is equal to b, why did I do that? Okay, let me just erase this part. If I say to you, for example, the nth root of a equal to b, what does this mean? This means that a or b is equal to a to the n, right? That's what this means. It means a times a times a n times gives you b, okay? Right. Sorry, p to the n. Sorry, p to the n gives you a. Sorry for that, guys. I was wondering now, this doesn't make sense to me now. I was thinking, how can I justify that? I couldn't. Okay, thanks. So yeah, if you raise b, it's a bit like this. It works like this. If I rewrite this thing, just rewrite it. If I rewrite it, this part here, if I rewrite this part, it's a to the 1 over n. Why is it suddenly like doing all that now?
Dr. Sears?
Yes.
My apologies.
Okay.
Students, I do see that Bui is saying that he can't see his screen. If
okay.
you are not able, no, it is your network. Because as long as, if any other students can see the screen, it means that it is your network. And not the network of Dr. CS. So I will indicate if there is a network issue from Dr. CS side, but any any other time, student,
Okay.
it will be your side and you will have to move around to get clear network. Apologies. Thank you. Continue, please, Dr. Sears.
Okay, I don't know why I'm having trouble with this pen now. Yeah, let me see. Let me just see, Shmaya. I shouldn't touch this board, it seems. I'll just. Okay, sorry. So let me just go back to this, guys. Yeah, just making the statement. Maybe just refine it a bit and say so. So the nth root of a can be written as a in exponential form a to the 1 over n, and it just means that if I say this to you, it's equal to b. It just means that b times b n times gives you a. Okay, why is that so? If you look at this, the nth root of a. Maybe some people need some persuasion as to the truth of that. If I say this is equal to b, and if I raise, this is true if and only if you raise a to the 1 over n to the n and b to the n, well, so then those n's will cancel there, and you're left with a equal to b to the n. So what I did in essence was to raise the two powers inside the bracket. I raise them to the same exponent n. Do you understand it, guys? Okay. Anyone who needs further clarification there, guys? Are you fine with that? Okay. Guys, do you need? Are you fine with that explanation there, guys?
Yes.
Okay,
Yes.
great.
Yes.
Okay, great.
Yes.
So my question now is: are there any other compelling questions that you need maybe to be answered on radicals? There are some other properties of nth roots too. For example, the nth root of a times b. You would have encountered this and you covered this section already. Can be written as the product of the nth roots of a and b. You would have encountered such results too. Okay, multiply, right? A times b. You can write it like that. And there's a similar thing for exponents. So a over b, the nth root of a over b can be written as the nth root of a divided by the nth root of b. I think it's intuitively plausible. It can happen that way. Makes sense. Okay. And then there's some other variations of this. There's some other variations of this where you have that the mth root of the nth root of a, right, can be written as the nth root of a. I think you guys would have encountered that in your assignments, perhaps. I don't know. And then another point is the nth root of a to the n, obviously, is just a, right? And then I think you would have encountered this one also. This is equal to a if n is 1. And the nth root of a to the n is equal to the absolute value of a. It's always positive if n is even. Those are some basic stuff that you need to employ to solve some problems. I think you guys would have encountered that. So my question is, are there any compelling questions that you have that you struggled with on exponents and radicals, guys? There are the laws of exponents also there. Sorry about that. And there's your radicals also. If there are no other questions, then we can just go on to another section. Okay, guys? Maybe we can look at one or two problems then, guys. We can just look at one or two problems of rationalizing denominators and stuff. There's this question called rationalizing denominators, okay? Look at this one, rationalizing denominators. I trust you guys are fine with scientific notation. We looked at radicals and some laws of exponents. There are some nice examples also in your textbook. I don't know if you guys are using a textbook where you have to rationalize denominators and so on. Did you guys encounter any problems in the assignments on that? So no one has questions on that. Okay, let's just do a problem quickly. A very simple problem, how to rationalize a denominator, okay? Let's just look at a simple problem. Let's just do a share there quickly. Just do a share. Let's just share the whiteboard with you guys. I just have to create something new there. Let's just go down here. How we rationalize a denominator, okay? So let's look at the notion of rationalizing a denominator. It falls under this section called exponents and radicals. So I'm going through this because I think some other guys already did this, so I just want to check their understanding of that. Right, so rationalizing a denominator. Let's suppose I give you a problem like this one, guys, and I ask you to rationalize the denominator. Well, in the first place, what is the denominator? Here, square root of 3. The numerator is 2. How would you write this problem such that the third form or the radical form is on top? Okay, guys, how would you write this 2 divided by the square root of 3? You can see that the denominator is an irrational number, okay? But now we would like to write this as a rational number in the denominator here. How would you rationalize this denominator? What would you do? You guys remember that?
Want to multiply?
Okay, you can answer.
We would multiply by the denominator.
Good.
By
on top and at the
square
bottom.
root of 3.
Great.
Both
square root of
the
3
top and the bottom.
Yes, yes. Otherwise, it won't make sense if you didn't include the bottom also, right? You will have an inequality occurring here then. Can you see that? Then you will, if you didn't multiply that in the denominator by square root of 3 also, you would have had an inequality. You can't say that the right-hand side is equal to the left-hand side, right? Of course, they are equal because square root of 3 divided by square root of 3 here is just equal to 1. And 1 multiplied by any number is just that number. Okay? Right. So on top, what do we have there?
2 root 3.
Times 3 to the half in exponential form, right? So it's 3. The bases are the same. So you add the exponents, which is just 3, which is just here. Can you see that, guys? Okay.
Right.
Some people ask you, but why square root of 3 times square root of 3? 3. But they are familiar with this law. It says a to the n times a to the n is a to the m plus n. It so happens that in our case, m and n are the same. Can you see that, guys?
Yeah.
Okay. So I normally try to explain it like that, and people seem to be happy when I say that to them. Otherwise, they don't like it when I just say square root of 3 times square root of 3 is 3. They ask me why. So then I just use the laws of exponents, okay? So my question is, guys, are there any compelling problems? Let me just look at some problems also, maybe to ask you guys, maybe you can think about it. Suppose I ask you a question to evaluate an expression. Let's say an expression like the following. Very simple stuff I'm asking here. Let's look at this example here. Maybe we'll do 2 examples and then I'll let you guys be, okay? So it's 25 divided by 64 to the exponent minus 1,5. People, you know that minus 3 over 2 is 1,5, right? People, you know that this is minus 1,5. You agree, no? Minus 3 over 2, right? So suppose I ask you to evaluate. I'm just checking your knowledge of exponents and radicals quickly, guys, before I move on to the next section. So how would you proceed with a problem like this, guys? Any guys, any person wants to venture an answer there? Or where would I start with a problem like this? Let me just erase this part. Just clarifying this. Any person who would like to venture an answer without a calculator, guys?
Manipulate the exponent.
Okay. I can't hear you.
Manipulate the exponent.
Okay. Okay. What does that mean if you say that?
You multiply by 2 over 3 on the exponent.
Okay, but what must I do to do that? I know what you're saying. You're saying something like this: 1 over 25. You can correct me if I'm wrong, because you're using one of those things that I wrote down on the whiteboard, the earlier whiteboard. You are saying that, right? You are using this fact: a to the minus m is equal to 1 over a to the m. Do you agree with me?
Yes.
That's what you're saying, right? Okay. And what would be your next step then? Can you see these? This 25 and 25 and 68 are perfect squares. Can you see that?
Yeah.
They're perfect squares. Can you see that? Look here. Let's just work with a denominator. 5 squared and 64. 64 is 8 squared, right?
Yes.
64 is 8 squared, right? And then I can raise this separately from that one to the 3 over 2. And this one separately to 3 over 2. Are you happy with that? Then I can do my cancellations. Because I multiply the inner exponent with the outer exponent. Right? So that I've got 1 over 5 cubed divided by 8 cubed. Right?
Mm.
Yeah, we're in agreement there. And then we can just invert that. So it's 8 cubed over 5 cubed. Right? And then you're done. I mean, of course, 8 times 8. Well, you get 2 to the, what is that? 2 to the 9. It's what is that?
512.
Yeah, 512 divided by 125, right? 512
yes.
divided by 12 divided by 125. Just double check it, guys.
Yeah.
See it right, right? Yeah. Look, there's one approach. There are other approaches too, but there's one approach. So yeah, there we've just used the laws of exponents basically. Okay, that's all. Right. Any questions there, guys? Okay. Let's just. I feel like I'm romancing a stone here, guys. You're not returning anything.
Sir.
Yes.
And
who am I speaking to now?
Emmanuel.
About what? Hi, Emmanuel. How are you? Yes, I was looking for you. How are you?
Yeah, you said 1 over 5 cube and over 8 cube. Did you see that
yes,
statement?
Yes.
And
yeah.
therefore,
no, you know where? Let me tell you where this comes from, right?
where did that one
remember
go? Because you know I can't see it anymore. Yeah.
Is it okay? Can you see it? Okay. So let me just do this quickly to answer you, and I want you to think about it. Do you remember that a to the m all to the n is a to the m times n?
Yeah.
Exponents, right?
Yeah.
Right. So I'm just using that. 25 is 5 squared. There's my a, 5. And my n is outside 3 over 2. So 2 times 3 over 2, well, the 2 cancels in the numerator and denominator. I'm left with 5 cubed. And the same applies to 8 squared, all to the 3 over 2. The 2 cancels. The 2's cancel. I'm left with 8 cubed. And then, of course, this is 1 over that, so I have to invert that fraction. Okay? That's all. So in essence, we've applied this, and earlier we applied that. Okay? That's what I put.
Okay.
Are you okay there, Emmanuel? Emmanuel, can you hear me?
Yeah, I can hear you.
Yeah. So my question is, can you see how I've allowed this to come into play here? Can you see that? A, my 5 is A, my M is 2, and my N is 3 over 2. So it's the inner exponent multiplied by the outer exponent. The same applies to 8 squared, all to the 3 over 2 is the inner exponent multiplied by the outer exponent, yielding 3 and 3 there. Can you see that? That's my point. Are you okay with that, Manu?
Hey, no, hey, I'm still lost.
I want you to think about it, okay? Write down the solution, and then write down this. I'm double ticking that one. It's an earlier stage. We use this first part. We use this part here. We used it here. And then the previous person.
Yeah, I understand the first stage.
Yes. So what I'm saying is that, and this part here, especially the denominator part, we've used this here. I want you to think about that, okay? Write down that solution and just go through it and see how we've employed that, okay?
Okay.
Yeah. If you want to, I can just write 5 over 8 squared, all to the 3 over 2. Again, all to the n.
Yes, yeah.
Can you see that? There's another
way.
Yes.
You
see that?
Yes.
And then you also have the 1 on top, of course. I just worked without the 1 now. Can you see that?
Okay.
Great.
Oh, no, thanks.
Great, no problem.
Yeah.
No problem. Okay. So guys, listen, I just need you guys to practice this and then come with questions to me also, so that I can just accommodate also the other guys who are ahead of us. And I want to hear from the guys who are ahead of us now a bit, because I don't think it's also fair. Some guys are busy with chapter 2 point something, so I really want to accommodate them also as far as possible. But I can't know that if they don't ask me questions also. I need to check. I don't want to assume. I don't want to assume stuff. So look, we touched briefly on exponents and radicals, not in its totality. Are there any of you guys who struggle with algebraic expressions in general? I just need to say a few things about that, some main results on that, algebraic expressions that you have to be familiar with. I'm just going to write it down on algebraic expressions. Let me just write down some main results and maybe do 1 or 2 problems, because you guys don't seem to ask your specific sections that you're battling with. So I'll take the liberty of entertaining others who might struggle with this. People, you remember that you have this result. And then ultimately you can reduce this to the difference between 2 squares. I think you're familiar with this, right? And you're also familiar with this because the middle term here in this first case cancels, okay? In the second case, you'll also be familiar with this kind of scenario. This thing you can't factorize under the real numbers. Maybe you can And you should also be familiar with this one. It said a minus b all squared. Now, a minus b all squared is a squared Let's look at this. Sorry. Right? This you can write as a cubed
Apologies.
plus 2 plus 3a squared b plus 3ab squared plus
Mark,
b cubed. Right?
sorry, we couldn't see
Hi.
your screen for a bit.
Is it? Okay, okay. Wow.
No, but I can see it. I can see it now.
Okay, great. Sorry. I think thanks for letting me know, because I don't know unless no one says, unless you say something, no? Okay,
Thank
great.
you.
So it's okay now, right? Okay. So I'm
Yes,
just
it's fine
writing
on
down
your
some
side,
results.
Dr. CS. It's network from the student.
Oh, okay, okay, okay. Okay, great. So, and then there's another fifth result, and there's some more results, but I'm just sticking to the core results here that you guys sort of have to know, like in your heads, you should have this, okay? It's a cubed minus 3a squared b plus 3ab squared minus b cubed. Those are sort of your standard results for algebraic expressions, guys, that you guys really need to know, like just off your head, just like that. Okay. We can maybe do one or two problems. Were there any problems you encountered while attempting some stuff related to this? On factorizations, etc. Were there any problems there, problematic problems, guys? Any problems there, guys?
I didn't encounter any on my side.
Nothing. Okay, thanks for that. Oh, so you are au fait, you know these things well. Any other person?
No.
Nothing. Okay, great. Let's maybe just try.
Mark, I just asked a question.
Hi.
I just want to know on the algebraic, the expressions, if you have to, like, if you get where you set equals, where you get the solution that is like broken down, how you get it back to the normal expression. I struggle with that part a bit.
Oh, okay. So it's like, okay, so now you're factorizing back, yeah. So,
yes.
So yeah, so the factorization. Let's do maybe let's just do one example, okay, and see, okay? Let's just do one example and maybe see where they write maybe 4 terms. Let's do 2 examples and just see how they put it back together as one term, okay? So currently here you've got 2 terms. To put it back as one term, this is what you do. Here we have 3 terms. Now it's 1 term. You have 3 terms. Now it's 1 term. So she wants to know how does one put all these separate terms back into the 1 term. Here we've got 4 terms. Here it's 1 term. Some factorization was employed. And in token here we've got 4 terms. Now it's 1 term. So let's just look at maybe 1 problem, 2 problems there. Let's just look at 2 examples that sort of reminds us of what we call, actually we call it factorization. Okay. Let's just do that quickly. Let's just do 1 or 2 problems with 4 terms. So here we've got x cubed plus x squared. Sometimes you have to group them. And then, but my point is, when they're in this form, you're supposed to remember this kind of form. You must remember these are the standard forms. You must be able to see it and know the result. So you must be able to work from here to here immediately. Okay. And from year to year, immediately, you should be able to identify that and go back immediately. But I'm going to give you a problem that relates to grouping of terms now, okay? I'm not sure if this will answer some of your questions, okay? Or your concern. Let me just use the eraser here. I'm just guessing that you might have these kinds of problems. Okay. So, for example, if you look at x cubed and x squared, well, x squared goes into x cubed x times, and x squared goes into itself once. And here I can take out 4, and 4 divides 4x times, and into itself, it divides there once.
Yeah.
Now I can, right? Yeah, can you see that? And x plus 1 divides into x squared times x plus 1. This remains. This cancels out, right? By the same token, it divides, x plus 1 divides into there, and 4 remains. And there's nothing else you can do here. This is an irreducible factor, this x squared plus 4. You can only factorize that in the complex numbers, okay? Not in the real numbers. So that ultimately, these 4 terms here, well, I'm just repeating this. It can be written like that. And no more factorization is permissible. It's irreducible for the real numbers. You can't factorize any of these 2 factors, x plus 1 or x squared plus 4 under the real numbers, okay? Does that in part answer some of your concerns there?
Yes, thank you, Mark.
Okay, let's look at one more, just for the sake of completeness as well, as far as possible. Let's just look at another example there. Oh, now it starts again. Let's see. What did I do? Okay, okay. Let's just do one quick one again. It's the same procedure, and then sometimes something nice falls out. Sometimes you have to restart and check. Okay, here's x cubed minus 2x squared. Sorry for that, guys. I pressed some button here. X cubed minus 2x squared. Minus 2x squared minus 3x plus 6. Again, we will look at terms to group together. Now, based on the powers here, I would take x cubed and minus 2x squared. So I would do this. Someone might try something else and it still work. It may still work. But for me, the natural choice would be to group those first 2 terms. And then lastly, well, I can just take out a common factor for minus 3x and 6. I take out minus 1. So that if I multiply minus times 3x, I get minus 3x. And minus times a minus gives me plus 6 there. So it's consistent, right? And what is my common factor for the first term there, guys, under the brackets? It would be x squared, right? X squared for this here, right? And then x squared goes into x cubed x times. And it goes into 2x squared, well, minus 2x squared 2 times, right? And then here, remember the minus sign there, guys? Remember the minus? So let me stay clear of that minus. I would take out positive 3 now, okay? I would take out positive 3. Positive times a negative is a negative, so I'm consistent, it's fine. So positive 3x goes in there x times, right? And it goes in that one. So this is a negative times a negative is a positive, so I need another negative here. So it's 2. And can you see there, guys? There's my common factor again, x minus 2. So that I have x minus 2 as a common factor. and it cancels there, and I'm left with x squared. Cancels there, and I'm left with minus 3. And further reduction of this into smaller factors is impossible unless you do irrational numbers now. But there's the two factors now. So we've condensed these 4 terms into one term here. That's the factorization of that. Is that clear, guys?
I have a question.
Okay, no problem. Let me just check the person who initially asked the question. Is she fine with this factorization?
Yes, thank you. I understand it better.
Great. Is this the kind of thing that you were sort of grappling with, I suspect?
Yes, definitely. Thank you.
Okay, great. Okay. So the previous person, they wanted to say something?
There, on the second step.
Okay. The step should be the step here, right? The step here.
Yes.
Okay.
Yeah, you said on the other one, -3, then open brackets x minus 2.
Yeah.
Can you go back to the first step there at -3x minus 6?
Okay. Yeah. Okay. Yeah. So there, I took out the negative. Yeah. Remember, there's this negative. You have to be careful. This negative. And then there's also the positive. Okay. So I have to be consistent when I deal with this negative and with this positive. Okay. Look, if you had taken out the positive, you would have 6 minus 3x, right?
Yes.
Then at some stage you'll have to go back, because you can either change x minus 2 to 2 minus x. Changing it on the right hand side, you'll have to take out another negative again anyway. Okay. So I anticipated that. That's why I said, let me take out -1. Okay.
Right. Okay.
And you can see when you do the multiplications, it's consistent. The right hand side, the far right, is consistent with the far right on the left. Can you see that? So it's minus 3x. We've got minus 3x. Negative times -6 is positive 6. So it's consistent. Can you see that? So you have to be wary of that. You must sure that. Otherwise, if that's not the case, you will violate equality. Then it will be.
Okay.
Great. So look, I mean, I was really hoping you guys might have some other solid questions on it, but it's fine. What Ms. Prim said, I am permitted to have a 1-on-1 or 2-on-2 with you guys also. But I'll tell you when that is possible for me. It's not possible all the time. But the best times would be probably Wednesdays and Thursdays. If you want to organize a 1-on-1 session, probably Wednesdays and Thursdays. Ms. Pram? Probably Wednesdays and Thursdays, but I will let you know. Because I suspect they have to come via you to make such an arrangement, right?
Yes.
Can you hear me, Ms. Pram?
Yes, I can.
Yeah, because I would really like to, at some stage, if it's one. Hello? Can you hear me?
Are you able to hear me?
Yes, I can hear you. I can hear you loud and clear.
Awesome. So yes, students are allowed to schedule a 1-on-1 session with you. It will be a 1-hour session, which is only yourself, the student. But these are the student books an appointment with me, and then we verify, and I schedule that between yourself and the student. All right, so I will then put a notice up to the students as to the available times, and they can then just make a bookie.
Yeah,
all right?
Either just maybe the best times would be, unless I tell you something else, but definitely Wednesdays or Thursdays. Okay.
All right then, students. I will then put my email address in the chat box so that you can email me for Wednesday or Thursdays when you are available. Obviously, that will not be from 4:30 to 6:30 because there is a workshop in session. So anytime before that. All right, so I will put in my email address and you can just email me should you wish a 1-on-1 with Dr. CS.
The reason why I'm saying that, Ms. Pram, was that I sense people are a bit reluctant maybe to pose their questions for various reasons. They seem to be hesitant, but they may have some questions.
Right.
But I don't want to preempt. You know?
Okay, not a problem.
Great. Okay, guys. So then there's the notion of rational expressions. Can anyone tell me what's a rational number here, guys? Because some of you have already gone far beyond chapter 1, I know. Does anyone venture, can anyone venture maybe an answer to the question, what is a rational number? Anyone?
It's a fraction.
Right. It's a fraction, right? But what can you say about the numerator and denominator? What can you say about them? More specifically, what should they look like? What should they be? It's a fraction is a numerator.
It should be
can you hear me? Hi, can you hear me?
Yes.
Hi, yes.
Yes, Dr. Sears.
Yeah. So a rational number.
The denominator cannot be 0.
Right.
Denominator.
But the numerator and denominator are integers, which are not in such that the denominator is not 0, right? So they're actually integers in the numerator and denominator. But of course, 0 falls under the definition of an integer. So when you say a rational number has the form r equal to m over n, both m and n are integers, but n is not equal to 0. You are right there, okay? Right. So in the same way, we define a rational expression, basically. It's the quotient of two polynomials, okay? Of course, when we do substitution there, we do not permit the denominator, the polynomial in the denominator, to be 0. So a rational expression is a special type of fractional expression. When you guys did rational expressions, did you encounter any serious problems? Have you guys already submitted an assignment or two?
Only assignment 1, assignment 2 is up in about 2 weeks.
Assignment 2 is?
Assignment 2 is due the 29th of May.
Is it? Okay. So it's due soon, okay? Less than 2 weeks' time. Okay. And can I ask you, up to where did assignment 1 go to?
Assignment 1 was about section 1, as far as I know. I don't have found papers. I'm quickly going to go get them.
Okay. Section 1. Okay. You guys were provided with the solutions of that assignment, I assume, right?
Yes, it was a quiz.
Oh, it was a quiz. Okay. No, it's fine. So section 1.1 was in section 1.1 of chapter 1.
Sorry, I think it's chapter 1. I'm just quickly opening the things here.
Yeah, it makes sense. I think chapter 1, yeah, it makes sense, yeah. So
yeah.
Okay. Okay. Look, guys.
Can I please ask? Is it possible to ask a question that's like a couple of pages ahead?
Okay, yeah, it's fine. I was actually waiting for you guys to ask me such a question, and I'll tell you.
Could you please clarify inverse functions on restricted domains?
Okay. So let me just talk about the theory of inverse functions. Okay. So what we assume with an inverse function, well, the function that you want the inverse of, I will just talk of them because I wanted to treat that in the next session that we have, okay? But let me say the following. So I wanted to go up to initially maybe 1.7, okay? But let me say the following. So with an inverse function, for an inverse function to exist, the function that you find the inverse of must be a one-to-one function, okay? And first of all, you know what's a function, right? I assume you know what a function is, right? Okay. Would that be a fair question to ask you? You know what a function is?
Yes, I do.
Hello? You do, eh? So function f from a set A to a set B is a rule of mapping such that for every x in element A, there's exactly one element y in element of B such that y is equal to f of x, right? So for one-to-one function, if f of x1 is equal to f of x2, then x1 implies then x1 is equal to x2, it implies that. Alternatively, if x1 is not equal to x2, then f of x1 is not equal to f of x2. So those are for one-to-one functions. So before you can deal with the notion of an inverse, you must first establish whether the function is one-to-one, okay? Then I'm not sure at your level if they also speak of onto functions or surjective mappings. Have you encountered that notion of a surjective mapping?
No, not yet.
Not yet. Okay. So we call one-to-one functions injective mappings. Okay. And then when for every y in the range there exists an x in the domain, we call that function an onto function or surjective mapping. So if a function is one-to-one and onto, you can always find an inverse. Okay. If a function is not one-to-one, then you cannot find the inverse of that function. So I want you to first look at whether it's possible to find this by establishing, before you find the inverse, whether the function is indeed one-to-one. Because a function that's not one-to-one will not have an inverse. Okay, that's the first condition. Also, I don't think you guys speak much of surjective or onto mappings. So I think you start with one-to-one as first. Okay. So I want you to revise that section, and then next week we'll look at that, unless you have a specific question that you want to ask. Okay.
No, it wasn't a specific question. It was just me being quite lost about it. But thank you.
Okay, so I want you to have a look at that, and then what we'll do is the next. I wanted to finish up to 1.7 today. But it's fine if you can't do that. It's okay. Let's just do a linear function quickly. Let's just do the inverse of a linear function quickly. Just to latch onto your question quickly, okay? I didn't want to do this yet, but it's fine. Our first one. So let's consider a function that looks like this. I'm going to ask you what kind of function is this. Let's just consider. So it's just an example of inverse functions, okay? So I'm going to state the definition of one-to-oneness. Example inverse functions. Inverse mappings, right? Inverses. So an important condition here is, we'll do a quick example on a linear function. A condition here is that f must be one-to-one. So my original function. Are
you sharing something, Dr. Sears?
Yes. Okay. Let me check again. Let me check. Okay. Let me share this. Let me unshare. Okay, let me go back. Right. Can you see the screen now? The whiteboard?
Yes.
Yes.
Thank you.
Great. Can everyone see that, guys? In particular, also the person who posed the question on inverses. Who asked this question?
I did.
So can you see the screen here?
Yes, I can.
Good. So the condition for this is the original function, for its inverse to exist, the original function must be one-to-one. Okay? Remember? So say let's call the function, let's call it f, and then look at a quick example. Let's call the function f, right? One-to-one function means f of x1 equal to f of x2 implies that x1 is equal to x2. So you tell me there are 2 points, x1 and x2, but it is such that if fx on x1 and x on x2, and they are equal, then that x1 and x2 must be the same. Do you understand the definition?
Yes.
You understand it, right? The same statement if I make the same statement, here's the same statement. If two ordinates x1 and x2 are not the same, then f of x1 is not equal to f of x. The function values cannot be the same. If the 2 points in the domain are not the same, then the function values cannot be the same. Okay, that's what it means. These two statements, it's equivalent statements. It's the same statement. Okay, when someone says the first part, the top part for me, he's also saying the bottom part for me. Okay, right. So let me now construct a little example and just see what happens there. I'm going to ask you a question, if you don't mind. So let's consider the simplest of functions, a linear function, say, okay? Suppose you have a function y equal to f of x. You guys can still see the whiteboard, right? Y equal to f of x equal to 3x minus 2. Right? Now we know that this function has a slope of 3 and a y-intercept of minus 2. Can we see that, guys, right?
Yes.
Can we see that?
Yes.
Yes.
Right. Right. And can you also see that if I have a point 3x1, if I say 3x1 minus 2 is 3x2, well, and I transpose the minus 2 from the left to the right, well, 3x1 equal to 3x, 2, x1 is equal to x, 2. This condition is satisfied. This condition here, in fact, both of them, because it's the same statement. So I said, let me assume that f of x1 is equal to f of x2. Then I show that if they are equal, then x1 must be equal to x2. Therefore, that's a one-to-one function. Okay, this line here is a one-to-one function. In fact, if you draw it, if you draw this function, you draw that line. Let's try and draw that line quickly here, guys. You will see the one-to-one nature in the Cartesian plane. Let's see quickly. Okay, there's my Cartesian plane. There's my y-axis and there's my x-axis. Let's try and draw this line quickly. Well, it has a y-intercept of minus 2, right? Cuts the y-axis there at minus 2. And if x is 0, well, y is minus 2. If y is 0, x is 2 over 3. Put y 0, guys, then you will see that x is 2 over 3.
Yes.
Right? And that line is a positive slope, so it goes something like this. And you can see the one-to-one nature of that. You can see the one-to-one nature of that. There is no place here on this line where you can find that the same x, that the two different x values has the same y value. Not anywhere on this line would you see that for two different x values, it has the same y value. Do you agree with that, guys? There's an x value, there's a y value. There's an x value, there's a y value. There's an x value, there's a y value. Okay? This is illustrated in this statement here. If f of x1 is equal to f of x2, then you will see that x1 must be equal to x2, which means it's one-to-one. Now, if you want the inverse of that function, so now we're all set to get the inverse of that function. Okay? We're all set to get the inverse of that function. So let's look at that function again. So the function was y equal to f of x equal to 3x minus 2. Right? From there, let's try to find, this is so if and only if. Let's try to find x in terms of y now. Right? Thus, when I do the manipulation, you guys will notice that y plus 2 divided by 3 is equal to x. Do you agree with that, guys?
Yes.
when I make x the subject of that equation, right?
Yes.
Can you see there? Now, if you interchange x and y, interchange x and y now. So for the inverse function, when I do the interchanging with x and y, because that's what happens, I get that f inverse is x plus 2 over 3. Those are inverse functions, okay? That's how you do that. So I just found the inverse. I've established whether it's a one-to-one function. I established that. And then I make x the subject of the equation. And afterwards, to find the inverse, I just interchange x and y. That's all I do, okay? Right. I think the person who posed the question should be happy with this answer. Is that fine?
Yes.
Okay. Let's see what will happen if we do a composition of these two functions. Have you done compositions? Have you done compositions of mappings, combinations? Okay. Remember what they say. You've done that, no?
Yes.
Have you done composition of mappings? Okay. So remember what it says. It says that f of f inverse x is equal to x, right? Let's see if we get this now. So we had f of x equal to 3x minus 2. Just erase that, sorry guys. We had, so I'm just double checking if our answer is indeed correct. Okay. So we had our original function, y equal to f of x equal to 3x minus 2. I want to check whether this condition is satisfied when I allow f inverse to be in the domain of f now, okay? All right, let's see what will happen now. Or the range of f inverse in the domain of f. So let's see. And we found f inverse of x. We found it as x plus 2 over 3. Now let me do the composition. Right. So what does f do? Anything that comes under f, right? It multiplies it by 3 and it subtracts 2. So now f inverse comes under f. It comes under that. What does f do? F will multiply it by 3 and then subtract 2. Okay? It will multiply it by 3 and subtract 2. Let's see. So anything that comes under f, it will multiply it by 3 and subtract 2. So let's see there. It multiplies it by 3. Oh, sorry there, guys. Oh, I've touched that. That's why it does that. Sorry for that. Yeah. So let me repeat that statement. So anything that comes under f here, and it's up to 2. Let's see. So it multiplies it by 3. And then it subtracts 2. As expected, there's the result. There's the result of that composition, guys. If you just want to make sure that your inverse function is correct, when f acts on that inverse function, it must yield us x, which is indeed the case there. By the same token, just here, I don't know why I always battle with us. Oh, sorry for that, guys. By the same token, if we now, you can also let f inverse act on f. So we'll do this in a bit of detail, hopefully next week. By the same token, if f inverse acts on f, and you can try this, it must also give you x. We did it one way, okay? So the person who asked an inverses, is that what you've encountered before when you read through the stuff, right? They will talk about these things, right? One-to-one functions and what is the result of the composition of f and f inverse? I trust that you've done it, right?
Yes.
Okay, great stuff. So hopefully next week we can entertain you a bit more with that. And also try to, the guys who are a bit behind also to accommodate them. But we're not done yet, so, okay, great guys. So
Yes.
rational expressions, great stuff, equations, and so forth. How have you guys, did you guys manage to have a look at equalities and so on, equations, solving equations?
Yes.
You managed to do that. So were there any troubling aspects of equations that you battled with? Was there any specific problem maybe you wanted us to look at? So next week we'll look at inverses a bit. Hopefully we can do that. And composition of functions. Graphs of functions, some functions here. And I'm just looking. So guys, in terms of equations, were there any problematic problems there?
On my side, no.
Nothing. Okay, great. Thanks. Any other person, maybe? I think it's section 1.5, yeah. Equations. I'm just looking for some problems on it quickly. I didn't really, I was hoping you guys would come up with some problems, and then we will look at that. Let's look at a particular problem, guys. Maybe one or two problems that I can select here on equations. I see some nice ones here. Maybe we can look at them. Just some from the exercises. Let's just look at one problem quickly, one or two problems. Let me just share the screen with you. Okay, great. Can everyone see the whiteboard, guys?
Yes.
Great. So suppose I have this little exercise, which I call an example. So there's a problem from the exercises. I just want to see what you guys propose I do with this problem. So suppose I say to you, there was this nice problem. I just glimpsed it. Determine whether the given value is a solution to the equation. Okay. Let's see quickly. So they give you the problem. They give you the equality. And maybe you've encountered it: x to the 3/2 divided by x minus 6 equal to x minus 8. So now they say to you, there are two possibilities. They ask you if is x equal to 4. Is it a valid choice? Or is x equal to 8 a valid choice? They ask you which of those ones would be a valid choice. Okay. So what do you propose? How do we start this problem, guys?
Cross multiply.
Cross multiplication is fine, right, guys?
Yes.
Guys, do you agree with cross multiplication then? I would do that. I would start with cross multiplication. Okay. Let's just see. So when I do that, I will x to the 3/2 x minus 6 with x minus 8 in the numerator on the left. Okay. Right. Then what next? What should you propose next?
Factorize. You multiply out.
You want to multiply?
Multiply out the brackets.
You want to multiply the bracket. Let's see what's going to happen. So on the right hand side, he proposes we multiply out the bracket. Is that correct?
Yes.
You should be happy with that.
Yes.
Okay, and then what would you propose next?
And then you're gonna move everything to the left-hand side and equate it to 0.
Yes.
Okay, let's see. She suggests that we move everything to the left-hand side.
Yes.
Let me take the highest exponent to the far left. But it's fine for now, doesn't really matter. This is what she is proposing. What next?
And then you're going to group them.
Okay, I agree. Which ones would you group? Which two terms at a time would you group?
X to the power 3 over 2 and x to the square together, and the 14x and the 48.
I was probably going to do the same
thing.
Okay, right. So normally I would take out the lowest of the powers here. I would take out x to the 3 over 2 because it's 1,5, it's less than 2, right? So she says she would take out x to the 3 over 2, right? And then what will I have there? 1 minus x.
So
yeah.
It's not 4, it's 14. So there's a problem.
14. Oh, thanks. I wrote down 14. I'm writing down 4. And I'm writing down plus, not minus. Look there. I've made an error. Guys, look here. He's reminding me that I wrote down minus 14 when I'm writing 4. And look here. I've changed things there. Can you see that? Thanks for that. Okay. Otherwise, we're going to have another big problem. Thanks for that, guys. Okay. So, so what do we have here now? So what do you propose we have here? Should I have a minus here? Can I take out the minus there?
No, it's correct. It's
right. Yeah, but I'm saying, can I? Do you?
Yeah.
Does this still make sense?
Dr. CS, are you still with us? Doesn't seem to be. Students, I think Dr. CS possibly have load shedding. Give me 1 sec. Okay, students, Dr. CS has definitely lost connection. I'm unable to get him on the phone as well. But we can continue next week, or if Saturdays are convenient for you, just put it in the chat box and let's see, who's prepared to meet on a Saturday and have a class on those days. So in the chat box, you can just put Saturday if you're for a Saturday class, and we'll see if the majority will rule then. Students, thank you so much for joining us today, especially for remaining until the end. And we hope that you have found this lesson interesting and helpful. And please do join us again next week. Are there any questions before I end the session?
No, ma'am, thank you.
Is there nothing? All right then, awesome. In the absence of questions, I then, all right, student Shadrach, you have a question?
I was just asking if we would be able to get the recording of today's lesson.
Yes, all the recordings first go for editing. So what I'm going to do is, if you can all just put your student numbers in the chat box, then unfortunately, I'm going to send you the raw recordings because it does take a bit of time for it to be edited. So that would probably only be available in about a month or so's time. I can send you the raw recording of today. So just put your student number in the chat box before you leave the class, and then we can do that still this week still. Is that okay with you?
I thank you, ma'am.
Awesome. Awesome. So students, please put your student number in the chat box if you want the recording, and then I will send it to you. So that then calls an end to this session. Thank you so much, and please do enjoy the rest of your.
Shmaya?
Dr. Sias.
Yes,
We were just ending the session.
Sorry, guys. Can I just say something, guys? I see that on that problem, I will then give this. I'll do the next session. I'll do the solution of that problem. I see I did the transposition, but I wrote some other things down. It's fine. I picked up the error. So and someone alerted me to that. But thanks for that. I transpose things to the left, but then I changed the signs again. But it's fine. So what I'll do is I'll send you the solution, guys. Okay. Or let me say, when I see you again, we'll do it together very quickly. Okay. And then what I hope you guys would do is also come up with some problems that you experience. And then I just have a brief discussion of the theory. It will help us a lot. Okay, guys? Thanks.